Welcome to this presentation. We are going to focus on photogrammetry principles and the relevance of those principles to the planning of field work to collect digital images which will be used in photogrammetry software. The software that we're largely focusing on is the 3DM Analyst suite of software, and it's broken down into two main components: 3DM CalibCam. This piece of software performs camera calibrations. It determines the interior orientations of the camera lens combination. Those interior orientations are key parameters for subsequent processing of the images. CalibCam can also determine the exterior orientations, the camera location and its orientation for any number of images that are loaded into a project. And CalibCam can create high-resolution merged images from images that are taken from a common location, a camera station. 3DM Analyst is the other main component of the suite of software from 3DM. It can generate, edit, and merge digital elevation or digital terrain models. It has digitization modes for digitizing linear features, planar features. We often do that in the stereo mode, and if you have a 3D monitor and 3D glasses, you can do it in a fully immersive 3D mode. We also use Analyst to analyze the data, do things like volume calculations, map or do automatic detection of planar faces. And the end products can be exported out of 3DM Analyst as 3D images or DXF files and ASCII files. So the workflow is to really, we have to capture some images in the field, and then we'll use 3DM CalibCam or 3DM Analyst, depending on how many images you are processing. If you're doing more than a single pair of images, you're going to start with 3DM CalibCam. And then in that processing, we will determine the camera locations and orientations. And then further processing, we end up generating digital terrain models and 3D images and point clouds. And then we can do some mapping and calculations and analysis of those 3D output products and export data to other software applications. So coming back to the principles of photogrammetry, the information that we need to determine the 3D coordinates in our model are the location of each camera's perspective center. That is essentially the center of the lens on the camera. We also need to know the orientation, which is the rotation of the camera about its perspective center with respect to some sort of coordinate system that we choose. And then we need to know the location of each matched point on each image. 3DM software will do these things automatically for us, either Analyst or CalibCam. Sometimes we're concerned about having enough detail in our 3D models. And really we're concerned about how large is a ground pixel. So is it going to be 2 centimeters, 1 centimeter, 10 centimeters? So we would typically want to know that before we go into the field. And with the objective to have a certain degree of resolution of the 3D object, we can now choose the appropriate focal length for a camera, as well as the distance between the object and the camera. So we can have the same ground pixel size with a short focal length camera located closer to the object, or a longer focal length camera located further from the object. So if you do have the ability to have different focal lengths, either by different lenses on the same camera, or two completely different cameras, you can choose the object distance, the distance between the lens and the object, to achieve the desired ground pixel size using this formula. So the object distance is the term distance in this equation. The focal length in millimeters is located as f, and so you'd put your distance also in millimeters. So this becomes a unitless ratio. You multiply it times the pixel size on the sensor. Each pixel on the sensor has a specific size, and that'll tell you what the pixel size will be in the 3D model or on the ground. And the accuracy of those 3D coordinates depends on the variation of the error in the pixels. And typically it's indicated by the sigma pixel, and the value is around 0.3 to 0.5 pixels. If we multiply that times the pixel size on the ground, and we found that from that previous equation, we can estimate the planimetric accuracy. And it's best to visualize this equation when flying a drone with the camera pointing vertically down, taking a set of pictures. We're using those pictures to build a 3D model of the ground surface. And so the easting and northing coordinates, the planimetric accuracy is governed by this equation. The depth accuracy depends on one more thing. Depends on the ratio between the distance between the camera and the object and the distance between the individual cameras for each image. So the base distance is distance between cameras. This term distance here is the object distance, the distance that the camera is away from the object of interest. And we take the planimetric accuracy and multiply by that ratio, and that'll give you kind of the accuracy in terms of depth. Or if it's a drone flight over ground, this will give you the elevation accuracy. And one can visualize this by looking at an air ellipse. And so here we have two cameras taking an image of the same object. The object, and one point on that object is where these light rays intersect. But there is a bit of variation in error in the actual images, and that's reflected by these dashed lines as they travel through the lens onto the sensor. So there's a little bit of a variation. Again, that variation is only around 0.2 to 0.5 pixels, but it makes a difference. That error creates an error ellipse. So that's the real location for the point of interest, but it could fall anywhere kind of within that orange ellipse. And if we want to reduce the size of that ellipse, we can do things like move the cameras further apart. And so by moving the cameras further apart, the separation distance or the base distance increases, and that improves our depth accuracy, because we can see the ellipse in that direction is now reduced. So we often need to give some thoughts to how far apart should the cameras be to get kind of optimal accuracy out of the 3D points. And as it turns out, if you move these cameras too far apart, the whole process starts to not work well, because the image seen from one camera looks vastly different from the image seen by the other camera of the same object. So they look quite different. And the image matching process within photogrammetry starts to break down. So there's a sweet spot by having them far enough apart, but not too far apart, to get the optimal performance out of your software. We often want to have the resulting point cloud in the digital terrain model georeferenced to a desired coordinate system. Think of it, maybe a UTM coordinate system. And often the best way to do that is to survey in ground control points that are captured in the images. And I'll show you what those will look like shortly. So if we have at least 3 known 3D coordinates that are captured by the images, we can move the resulting point cloud and digital terrain model into a 3D georeference coordinate system. The control points can be things that are captured within the image, so objects on the object of interest that have known coordinates, and or they could be the actual surveyed camera station locations. That's one way of getting a fully georeferenced end product. A simpler way where we may not need to worry about having the end product georeferenced is to use a vertical scale bar. So you can create a properly scaled model and with the vertical part of that model being vertical, matching vertical in the field by using a scale bar. Its easting and northing will be arbitrary, but that may not be of relevance as long as the 3D model has a proper scale and is vertically aligned. So here's some examples of what a scale bar could look like. Of course, if you're going to use a scale bar, it's important to have it vertical. So have some way of measuring the verticality of that bar using a hand level or other device, and have a known distance between targets on the scale bar. So we've got the red targets with a black center. I've got little black bands. Each of these is exactly 1 meter apart, center to center. If you look very closely, you can see there's a white dot in the middle of each black band. And here's a very simple scale bar. That's a 1 meter from black band to black band. You take a hand level, you poke it into the debris, move that stick around until it's vertical. And now you have to capture these scale bars in more than one photograph from more than one camera location. And if you do that, then you can use the scale bar to scale the model and make vertical. If you're using ground control points, so maybe you want to fully georeference your model, here's some examples of ground control points. They can be permanent things that are mounted and with a known coordinate, or they can be displaced temporarily, like what you see in this image. And then you have to survey those in, typically using a total station. And 3 is the minimum number, and they should not be collinear. So these are kind of on an arc, but they're getting close to collinear, so it's not an ideal situation. It would have been much better to have one of those much higher up. Of course, the practicalities of the field work dictate where you can place these things. But you have to try to create these in equilateral triangles in terms of their distribution, because they function much better for georeferencing a model. So we have different ways of making models. The simplest is this way. You have 2 camera stations, there they are. You have an object of interest, and you take a single photograph from each camera station. The cameras have a certain base distance apart, and they have an object distance. They have a certain distance between the cameras and the object of interest. And it's simple as that. So of course you try to orient these 2 cameras so they converge onto the same area. So the area coverage is more or less the same from both camera locations. And that gives you the biggest area of coverage in the 3D model that will be made from those 2 images. The camera base distance, the separation between these 2 cameras, depends a little bit on how rough and angular this object is. The camera base distance should be about 10% of the object distance. If it's let's say a rough rock face with indentations and protrusions, you're going to have that about 10% of the object distance. However, if this is a relatively planar feature, you can take your separation and move it further apart, enhancing your depth accuracy by doing so, and still have great performance out of the software. So it's a little bit of a trial and error to to figure out what is the appropriate base distance. Your object distance is pretty much dictated by looking through the viewfinder on your camera and seeing, okay, yes, I've got the whole extent of the object of interest in that one photograph. So now you're far enough away. Do the same at the other camera location. Also note how both camera locations are, if you connect a line between the two camera stations, it's parallel to the object of interest. That's best practices. You want these to be roughly parallel to the object of interest. There's no point in having this camera station located way back here and this one close. Having one very close, one far away is really poor practice for gathering those images. So, you stand in the field, take an image, walk over, grab another image. Of course, this makes sense if you're doing it with your smartphone. If you have a good quality digital SLR camera, that probably also means you have a tripod, and you should use a tripod as a means of holding that camera, because you do get better quality images. And those images are now brought into the software, and if you have ground control or scale bars, that information is brought into the software, and that you'll experience later. And you end up building a 3D point cloud and a 3D digital terrain model, kind of as illustrated here. So, what are some of the advantages or pros for simply taking two photographs, one from each camera location? It's simple. It's conceptually simple. It's easy to perform. Your depth accuracy can be adjusted by changing the separation between these camera stations. And you can use it for lenses of any focal length over any distance. You just have to adjust, either you stand closer or further away from the object, depending on the length of your lens. There are slight cons to that method. Each model, a model is this 3D thing that's created from that pair of photographs. It needs to be fully controlled with at least 3 known locations if you want it to be fully georeferenced. Or it needs at least a scale bar captured in both of those images if you're going to use a scale bar. And if you have poor ground control, you don't have much redundancy if the surveyor of that ground control made a mistake. So this method is vulnerable to bad ground control if only a few control points are used. Another way of collecting the images in the field is to do it as a fan from each camera station. So you end up in this situation, you really do have to have a tripod. It's hard to do a fan just standing and holding a camera. You introduce a lot of errors into the analysis if you attempt to do that off of just free holding a camera. So the camera gets mounted on a panorama tripod head on top of a nice stable tripod, and then you can rotate the camera. The graphic is not very good because ideally the camera, if the end of this little triangle is meant to represent the nodal point or the perspective center of the lens, that should be exactly the same location for both of those photographs. So you're supposed to rotate it exactly about the perspective center of that lens. So the graphic is showing poor practice. The best practice is you rotate it about the perspective center of that lens using a panorama tripod head. And then you capture not just one photograph, but 2, 3, or 4 to capture a larger length of the object, for example. And you can pan horizontally, you can pan vertically, and so you can often use a longer focal length lens to do that type of work, which means you got higher level of detail, smaller ground pixel sizes through that process. because you are taking in photographs of just small sections of the object in each photograph, but each of these sections, each of these photographs is going to overlap, and we can use them in the photogrammetry software to recover the full area of that object of interest. That's an image fan. Some of the pros: fewer unknowns, give strong orientations with very few control points. You need 3 control points captured in from both camera stations, for example. We can rotate the camera to capture the area very quickly, and it may be faster than relocating the camera, allowing large areas to be captured. In some cases in the field, you may not have the ability, you may be restricted as to where you can set up your tripod, but by fanning it, you can kind of cover a larger area from the areas where you can or are allowed to set up your tripod. The fan of images collected at a single station or a tripod location can be merged in CalibCam to create a high-resolution single image. And that's kind of handy if you have a cheap camera, doesn't have a wide field of view. You could come close to the object of interest. You can do a bit of a pan, taking multiple images, and then they all get merged into a much larger image. A third way of collecting photographs in a field is by doing image strips. And this is best illustrated or thought about when you're using a drone. So if this is a vertical profile, that's the ground surface, you're flying along with your drone, snap, grab an image, snap, grab an image, snap, grab an image with lots of overlap. And our drones that we use for photogrammetry purposes, you can pre-plan a grid pattern to fly the drone. So it flies in the grid, taking photographs, and you can control the amount of overlap between each subsequent photograph before you even go into the field, so you can have optimal overlap. Kind of a minimum overlap you need is illustrated there, 60% along the thing and along a line of photos, and maybe 25 between rows. If you're using drone imagery with structure from motions software, higher overlap is typically used. You're probably looking at around 75 to 80% overlap. And it's easy to achieve. It's fast to take lots, hundreds or thousands of photographs with a drone with plenty of overlap of the area of interest. Some of the advantages of running as a strip, you get accurate exterior orientations with very few control points. You only need a control point for maybe 1 out of 5 images. So you don't have to have a control point in every image. That control will be carried from one image through the images that don't have control within the software itself. And this is an ideal way for doing drone imagery using short focal length lenses. Let me come back to this. So if this was now a plan view, and this is, I don't know, a vertical rock face, this is a good way of also imaging the rock face. You walk along parallel to the rock face and stop, take a picture, walk, stop, take a picture, walk, stop, take a picture. And you just keep working along that rock face, and you can build up a model of a very long rock face using this approach. Okay, so before you go in the field with your camera, we should at least think about the camera settings. You need to know a little bit about photography and your camera settings. And you need to know some of these things to actually input into the 3DM CalibCam software. So everyone should be able to track down the approximate focal length of your lens. Whether it's a smartphone, a digital SLR, a drone, they all have a focal length, the physical distance between the lens and the sensor, and you need to know that. at least as a starting point, you need to know it within a millimeter, and then the software will determine that focal length at a much higher degree of precision. You need to know the sensor size. How big is your sensor? And we often want to know that in millimeters. So what's the width and height of that sensor in millimeters? It seems like a simple thing to track down, but go ahead and try to find that for your smartphone. Oftentimes they'll give you a diagonal sensor, or they'll say the sensor is 1 over 1.5 inches or something in size, but that is actually a diagonal dimension, and it's an approximate dimension. But we would really like to know the sensor size in millimeters, but to 2 or 3 or even better, 4 significant digits. Sometimes you can find out the specs for what is the size of an individual pixel on your sensor. You know, it'll be a certain number of microns wide and high, and most sensors on cameras are square, so the width and height of that individual pixel on the sensor will be the same. And then if you know the number of pixels, number wide and high, which is a pretty easy thing to find, you can multiply the size of an individual pixel by the number of pixels and recover this width and height. So you're going to need to know that. When you're using your camera, there's various ways and settings on your camera, but take advantage of what that sensor offers and use the maximum sensor resolution. Take the largest image possible. Some phones have like a panorama setting on the camera. That panorama setting doesn't give you extra pixels on either side of an image. All it does is crop an image, so it looks like it's a panorama because it's not very tall and it's very wide. It's a bit of a gimmick. Don't use it. You want to use the maximum sensor resolution to store your image. So after you take an image, take a look. How many pixels high? How many pixels wide? Does that match the sensor on your camera? You do not want to use digital or optical zoom settings on your lens. That's going to cause all sorts of grief and confusion in the photogrammetry software. So if your camera does have a zoom, you want to zoom all the way in or all the way out and leave it fixed at that position for all photographs that you take. And you typically want to shoot with your camera or phone in a landscape orientation. So it's wider than it is high, the image that's recorded. Most people carrying phones around tend to take pictures of other people, and that's in a portrait orientation. But for civil engineering, geotechnical engineering applications, we typically want it to go wide. There's no point in taking a picture of a bunch of sky or a bunch of I don't know, pavement or at the foot of the object of interest. We want to capture as much of that object of interest as possible in each image, and landscape is often the way to go. So now we have to think about these camera settings again. This zoom feature I said. Zoom is going to have the biggest single effect on the calibration accuracy if you have a zoom lens. And so we want to make sure the zoom is consistent with that used for calibration. And that generally means you can only use the very minimum or maximum zoom setting on your lens. Don't use anything in between, and don't change it as you go along the object of interest, taking additional photographs. Prime lenses, these are lenses that have a fixed focal length, are what I use on my camera. I have multiple prime lenses. They weren't cheap. They are very good quality lenses. They give a sharper and better quality image than a zoom lens. And well, you can't accidentally use the wrong setting because it's a fixed focal length lens. We want to make sure that that the focal distance is consistent with that used in the calibration. For most geotechnical applications, your lens is going to be set essentially at infinity. The focal distance is going to be infinity, but that could change if you're taking photographs in a confined space, a tunnel, or in a building. And so as your focal distance changes a little bit, it also actually changes the calibration parameters for that lens. And so normally you want to simply focus at infinity and leave it set at infinity as you collect your data. Because the depth of field on most of these, particularly on smartphones and point and shoot cameras, is actually pretty wide because they're, you don't need to worry about changing the focus from the infinity setting. You can use the autofocus, but make sure that it's not accidentally switching. Some cameras allow you to turn autofocus off after you've focused on infinity. Some lenses, including my fixed focal length lenses, allow you to focus what's called beyond infinity. It's not what you want to do. You want to focus it at infinity and just leave it fixed there. And because my lenses are all calibrated with that setting on those lenses. Your camera will have a variable aperture. And so the aperture that's used to capture the image could have a little bit of effect on the accuracy of the calibration. It has an effect on the crispness and clarity of the images at the pixel scale of your images. And it's often best to have your aperture fixed and left that way. And there are settings on cameras that lock the aperture to a certain setting. And f1/8 or f/5.6 is a pretty good place to start with a fixed aperture, and just leave it that way on your lens. Remember that as you reduce the aperture, that's the physical size of the lens that light can pass through. We get a bigger depth of field. And that might be important if you're doing photographs very close to objects. But if you make the aperture too small, the light that goes through that small little pinhole on your lens starts to refract around the edge of the aperture and starts to blur the image. So if the aperture is too small, it blurs the image. And so, they recommend a range is around focal length divided by 5.6 or the 2 focal length divided by 11. And my lenses are, I think, calibrated at f/8, and I also have calibrations at f/5.6. So for a digital single lens reflex camera, f/8 is often the best setting. Your cameras, if it's a film camera, we had ISO speed ratings because you actually bought the film for different speed ratings. The digital cameras emulate that a little bit. And so you can change that on your camera, and you can change it to ISO 1000, for example, if you're trying to lock a speeding race car, stopping the blur from a speeding race car as it zips past. But for photogrammetry purposes, we typically don't want to do that. We want to use often the lowest ISO rating, the lowest number. So it may be 100 or maybe a 50. We want to use these very low numbers for capturing our images, unless we are doing work in very dim light conditions, for example, underground where the lighting is poor. Then we might go up to a little bit of a higher number. We would certainly go up to a much higher, a much longer shutter speed, shutter time. So use a low ISO speed setting. Keep the aperture fixed. Those are two things you can set up on your camera before you go into the field. And then essentially you allow the camera to control the amount of light making it on the sensor using the shutter speed. So you keep the aperture and ISO speed setting set as a constant, and the camera, the light meter in the camera will determine what is the appropriate shutter speed to have appropriate amount of light coming onto the sensor. Of course, if you're doing work underground, your shutter speed may be really slow. I've done work where you activate the shutter and you wait for, it was either 8 or 16 seconds. So the lens is collecting light arriving on the sensor for 16 seconds before suddenly the shutter closes and the image taking process is over. That's painful, waiting 16 seconds for a camera to take an image. And of course, when you do that, everything's on a tripod and it's remotely controlled, so you don't have any vibration. On a bright sunny day with an aperture of f/8, ISO 100, your exposure times are going to be around 1/200th of a second or 1/250th of a second. And that's a fast enough shutter speed that if you kind of hand hold the camera kind of firmly and carefully, you'll get pretty good quality images. If it's overcast or early in the day, late in the day, or if your shutter speed starts to drop below 1/200th of a second, that's where a tripod comes in handy. So try to use a tripod. And then consider using a remote shutter release, some mechanism to activate the shutter such that the camera is not vibrating while it's collecting the light through the lens. If lighting changes over time between collection of images, for example, you have a huge delay, you decide to go for lunch halfway through your campaign, and so there's an hour gap, well, shadows and things are going to change. The length of the shadow on the object are going to change, and that starts to create some image matching problems. So you really do want to capture all your images quickly, all at the same time under constant uniform lighting conditions. And the software can compensate a little bit for that. And the best lighting is kind of midday under high uniform overcast conditions. If it's low light, you do not want to use a built-in flash on the camera. Definitely not. Because that means from one camera location, the shadows are going to look completely different than they do when you take an image from another camera location with a flash. So if you need lighting, it's not going to be lighting that's on the camera itself. You're going to have some fixed lighting in an underground environment to provide the illumination so that the shadows and the locations don't change as you're collecting your images. One interesting thing about the photogrammetry workflow and processing stuff, if something like a person or a car gets captured in an image, but you happen to have lots of images, that person or car will not end up being present in the resulting point cloud in a 3D model. So for example, if you're flying a drone over a highway and you're interested in building a 3D model of the highway, a rock cut or something, and cars go by, or a person on a bicycle goes by, of course that person will be captured in some images, but as long as you have enough images without that person or car present, the software will automatically discard the presence of that person. Sometimes it's partially discarded. You sort of see a bit of a ghost of that person in the resulting 3D digital terrain model. So some best practices. Take multiple photos from different vantage points that cover the same area of interest, and you can do it as an independent convergent model with basically 2 photographs from 2 different stations, or you can have 2 different stations and start to do a fan. But if you're going to do a fan, you need a panel head on a tripod, or you can walk along the object of interest, parallel to the object of interest, turning your body 90 degrees and collecting a strip of photos. And we're going to need a minimum of 2, and often we're using more than 2 to build up the model that we want. Shoot from locations that are parallel to the object of interest. This is important. I say it, all the time to people that are new to this, and they forget that in the field. Sometimes they're standing too close and sometimes they're too far away from the object. You should be the same distance away from the object each time you take a picture. If the object is curved, maybe the object is a huge sphere. Well, walk around the outside of that sphere at a constant radial distance from the center of that sphere. Then you'll get a good model from those images. So attempt to keep your camera pointed perpendicular or close to perpendicular to the surface. Obviously, if you're doing a fan type project, you're going to have the camera sometimes perpendicular, sometimes on either side of perpendicular as you fan the camera past the object. Don't shift your camera stations too far apart. As I said, about 1/10 of the distance that you are away from the object. And I add the note, this is important. People that are new to photogrammetry will tend to walk far too long a distance before they take their next photograph. You only need, in many cases, 2 or 3 steps. Then you take your next photograph. Think about it. Your eyes are only a handful of centimeters apart, and you can do a pretty good job of seeing distance and stereo. The photogrammetry will do okay. If your cameras are really close together, it'll do fine, except that your depth accuracy will be somewhat diminished. And so often for things that I'm involved in, just something the size of a house or something, or a building, I may be just 3 meters apart for each camera station, and I may have 5 or 10 or 20 camera stations. I just walk along, take a picture, walk along, take a picture. Avoid capturing sky or background objects that are, miles or kilometers behind the object of interest. So if you can try to frame the image such that you're capturing what matters and not stuff that doesn't matter, it helps a little bit on the processing. So now you're only processing pixels that are important and not moving clouds or trees or buildings that are far behind the object of interest. And once you do all that, you're ready to do some field work and start to acquire some images. So here's a tunnel. That's me standing there. I use photogrammetry to survey that tunnel as it was being excavated. So think about what we've talked about, and think about how you would set up your camera stations, where you would set them up, how you would adjust the camera settings to be able to survey both the portal area, and then as you go into the tunnel, how would you set up your camera to acquire those images? And with that, that's the end of this presentation. Thank you.